On in.
Professor,
Yes. What's up?
have you gotten a chance to look at what was up with my practice final?
Yes, I thought I corrected it. Let me double check on that. That's not good. Let me let this person in
Double
too.
check as well.
So let me see. Yeah, there was a problem with it, but let me go in. I'm actually going to go in through yours in particular and see. Grab that. Okay. And it's Jacob Haley, right?
Yeah.
Gotcha. Let's see. Let's see. Let's see.
Is it because it gave me 5 1-point question and then one 15-point question and then nothing else?
Yeah, that's okay. So it's showing everything else. And when I went in here, it looked like, oh, okay. Now I see. Oh, there was a whole window that wasn't loaded. I just thought it was waiting to load, but evidently, no, it never loads. So yeah, you got
Huh.
6 questions. One was worth 15 points. Oh, Jesus, that's not good. Have you tried to take it again since then, or is this the only time?
No, it only gave me one attempt.
Okay, now it's really jacked up. All right, let me do this then. Think I might know what happened. I've clicked on the actual test now to see if I can adjust it. See, it's showing all the points like it's working. It only allowed one attempt, so I don't know how that got toggled. Okay, now it should allow you more attempt. Oh yeah, okay, so everything's missing. God, Jesus. Okay, that's not good. That means everybody's had the same problem, and it worked.
Uh,
Man. Okay, so I will fix this. I'm glad I went through it this way because I would have never found it to be a problem, but it clearly, obviously, is a problem. So I will fix it right after class, and hopefully y'all can check it shortly thereafter and make sure it's actually quote unquote. So if anybody, you in particular would be great, but if anybody else can too, that would be awesome. All I need is just one person to check it out. I'm going to pull open the original one I made.
I'm sorry, what is this? What is this you're talking
It seems like, and actually it probably should be everybody's. There's a bunch of questions missing on the practice final. So
about?
I'm
Oh,
in
okay.
the process of fixing that, which I have to do after class, but either way, I gotta fix it. So, and it wasn't
okay, thank
allowing
you.
but one attempt. Yeah, I'm sorry, Jacob. I don't know if I went to the wrong class or what, but there was a module that was loading and it had the little ticker thing on it. So I assumed it was working fine, but evidently it was not. And it only went through question 6. So yeah, this will be fixed right after class. I will take care of that. Y'all might want to try to take your exam on Monday as opposed to Wednesday then. Of course, all those times are available to you. I'm thinking maybe Monday. I can also allow a 5:30 time. I didn't necessarily want to, But I think in light of this, that should be what I do. So I'm going to allow anybody that wants to can be on campus Monday at 5:30 and take it at that time. So in addition to those times I sent you, Monday the 29th at 5:30 p.m. at JC Building in Virginia Beach will be allowed. So hopefully that'll help. If you guys can't get there till like 6, that'll be fine. But I'd have to have you start by 6. So hopefully that'll help. But I'll fix this with that and then give you all that opportunity. Anybody else have any questions?
Thank you.
You're welcome. Sorry, Jacob. That's really jacked up. Yeah, that's not cool at all. That means the whole weekend I've wasted for you. I'm sorry. So sorry.
I have a question.
Yes, ma'am.
What homeworks are due when?
Okay, so here's the deal. I am in the process of doing a little bit more lenient stuff, but basically you only have to do, these are the ones that are only required, and I got a caveat to it, but basically 1 through 11 and then 14 and 15. So chapters 1 through 11, 14 and 15, those are the ones you have to do. Let me explain about 14 and 15. You have to do it because my intent is hopefully all my students will do chapters 14 and 15, and I can look at the homeworks and see that y'all have gotten good grades, and I can look at your practice test, which obviously I can't look at now, but I will look at it and I'll see that, you know, everybody's taken it a couple times and gotten some decent grades. That would give me enough comfort to say I think they've learned enough about 14 and 15 for me not to put it on the final, and then I won't put it on the final. Okay. My ideal scenario is they will all be due by 11:59 p.m. on the 28th. But I'm probably, just to give you an extra day, I'm going to make them due at 11:59 p.m. on the 29th. At least the 14, 15, and all the subsequent extra credit ones. Any chapters outside of 1 through 11, 14, and 15 are just considered extra credit, even if they aren't marked extra credit. So you can totally get free points that way. And by doing it, I'll probably find some other way to give you the extra points as opposed to just erasing your low grades on homework scores. Does that help you, Jennifer?
Yes, thank you.
No problem. You're welcome. All right, so I had a plan.
I had one question real
Yes,
quick.
go for it.
So what are we doing today and tomorrow then? Like what chapters are we covering? Just 15 or?
That was what I was getting ready to talk about. So my intent was just to show you the important parts of 14 and 15, show you, you know, all of it really, but show you what's important for you to make sure you can do for the practice test, as well as for what could possibly appear on the final. But like I said, I'm trying really hard to give you guys the opportunity to show me that you can take the practice test and do pretty well. And if I see that, then I feel comfortable with not putting 14 and 15 on it. But either way, if I do put 14 and 15 on it, there's some very specific problems that I want to show you that we're going to do. So that's all we're covering today. I just talked to Ms. Raskovic, and she said she was offering the exam on Tuesday or Thursday. I asked her if she could do Thursday, not Tuesday, specifically so y'all have a couple more days. And she said she'd do that, but she'd make 242 and 241. I'll take it the same night on Thursday. So that's her plan, is Thursday she was going to take it during your lab time. So you can still do that if you want, but what I'm telling you guys is I will allow you, if that's not good enough, given the screw up on my practice test, if that's not enough time for you, then by all means wait and take it Monday, and you can take it Monday at 5:30. That's as late as I can offer it, but it is Monday, and you guys are normally at lab on Tuesdays, but at least it's during lecture time, so hopefully you got that time allotted. I can allow you as late as 6, but not any later than that.
We're at Thursday lab.
Yes, you have Thursday lab, yeah, but she's doing everybody 241 and 242 will be taking it on Thursday as opposed to Tuesday, because I really didn't want anybody to have to take it Tuesday. If you want to, I mean, she might be able to accommodate you, but I think her plan.
We were never Tuesday. We were always Thursday.
Gotcha. Yeah, I'm just saying for the 242 is supposed to be Tuesday, so that's why. But she was
Oh, okay.
doing it for both classes.
Yeah.
So, all right. Anybody else? Okay. Well, let me quickly show you what's going on. Okay, and then I can from that explain to you what the most important stuff is. I can even pull up, for instance, some of the actual problems from my test bank so you'd have a better understanding of exactly what I mean. So I'm going to go ahead and share my screen with you guys. And we started talking about harmonic motion last time. And I even wrote the differential equation, but the main thing is I need you guys to understand what the differential equation is and be able to treat that in the abstract fashion. So that's one of the things that algebra is supposed to teach us, is to be able to think in the abstract. And to think in the abstract, you should be able to see equations as having a certain form, and anything that matches that form is also going to have the same solutions. So that's what I wanted to show you. So right now, if we use Hooke's law, which says that F is equal to negative kx, and we use Newton's second law, the summation of the forces is equal to m d2x, or let's call it d2r over dt squared, where r is the general position vector. They're just using r so it doesn't look like x or y or z. Okay, if you make that into one dimension, you end up getting negative kx is equal to m d2x over dt squared. And that's, again, for m equals a constant. So I can simplify this, and we generally do, so that the leading term is the one with the highest order derivative, and it has no coefficient in front of it. So I can do that by putting everything on one side of the equal sign and by dividing through by mass. And when that happens, the negative kx becomes positive kx on the right-hand side. But by dividing by m, you get positive k over m times x is equal to 0. So what I want you to see is a second order derivative plus a constant times the function is equal to 0. That's the form. Okay, second order derivative plus a constant times the function itself. In other words, we're taking the second derivative of x with respect to time, so the function would be x of t, and the second order derivative would of course be, another way of writing it would be x double dot of t. When you put a dot over something, that's a derivative with respect to time. When you do a prime on it, that's a derivative with respect to x. So y'all see that that's what I mean when I say the form of an equation. Now, if you were taking this in differential equations, they generally start off with, say, let's take a hypothesis, let x of t equal, and they'll say something like a e to the rho t. And what you quickly discover in that class, and hopefully from your algebra in the past you knew a little bit already, you figure out that if you take e to the I theta and add to it e to the negative I theta, that turns out to be, in fact, 2 times cosine theta. And if you do e to the I theta minus e to the negative I theta, that turns out to be 2i times the sine of theta. And all of that comes from Euler's formula. E to the I theta is equal to cosine theta plus I sine theta, which you can get from just doing a Maclaurin series expansion on cosine, a Maclaurin series expansion on sine, and a Maclaurin series expansion on e to the x, and then replace x with I theta. Okay, if you do that, then you'll see this thing is true. And from this thing, you can obviously put together the other two. So because that exists, this a e to the rho t turns out to be something equivalent or somewhat equivalent to a sine function or a cosine function. So this is what you would do in diff EQ. Okay, so in differential equations, you do that, and that. In physics, we sort of say, hey, you know, if I put a mass on a spring, I know the mass is just going to oscillate back and forth. And that sure looks like a sine or a cosine function to me. So what we do instead is we say, let x of t equal to some constant times cosine omega t plus an arbitrary phase angle. And it turns out that this guy and this guy can come from the initial conditions. So let me make some sense out of that for you. So you realize that this is what we call a second order differential equation. It's a second order linear differential equation. It's in fact a second order linear homogeneous differential equation, because if you put the variables that you're taking the derivative with respect to all on one side, in other words, all the x's on one side and all the x prime or x derivatives and all that on one side, if the other side just has zero, that makes it homogeneous. If there's no x or dx dt times dx dt or dx2 over dt squared times dxt dt, if there's none of that, you can assume that it's going to be linear. So that's nice. So that's why it's called a linear second order differential equation that's homogeneous. Now, the fact that it's a second order derivative means that the derivative has been taken twice. Does anybody know mathematically how you can undo a derivative?
Let's do antiderivative.
The antiderivative, which another word for that is the... Exactly, Jennifer, it's an integral. And what happens when you integrate with no range of integration? Like you don't have a bottom subscript on your integral or top number on your integral. What
Just
do you...
like you add like a c or something, or add an extra variable.
Exactly. You get an integration constant. That is really something that's necessary. You've actually got to figure out what that is to make sure it matches the function. So if you had a second order derivative, that means you're going to have to integrate twice. So how many integration constants do you think you're going to have?
2.
Yep. So what that tells you is, since this is a second order differential equation, then you're going to have two initial conditions. The initial conditions are often like, but not always, they don't have to be this, but we sort of always call them initial conditions, but they're often like x of 0 is equal to x0, and then you'd say and x, or excuse me, dx dt evaluated at x equals 0 is equal to 0. That's a typical condition. So that those are two initial conditions that would allow you to determine two constants. Another one is that x of 0 is equal to 0 and dx over dt evaluated at, or excuse me, I'm supposed to say evaluated at t equals 0, but I ended up writing x equals 0 in both cases. So let me fix that. So this is evaluated at t equals 0. This is evaluated at t equals 0. In this case, it's going to be v0. So that's another typical one, and those are the easiest ones to deal with. But in general, it could also be x of 0 equals x0 and dx over dt evaluated at t equals 0 is equal to v0. So all of those are valid ways of doing it, but they're initial conditions. And because of that, they allow you to determine what A is and what phi is. That's the way differential equations are solved. You hopefully you have an idea of some way of taking a finding a solution. Sometimes it's because it fits a certain form, so you know it's going to have a specific form of an answer. That's what we did here. And then you have some enough constants that you have to put in it so that it can account for the initial conditions. That's why I have 2 additional constants. Notice it looks like I have 3 because I have that omega there, but what you're going to see when I plug this equation in, you're going to see that that omega becomes something very specific. Okay, so that's really the process. Now that I have that, I'm going to say the first derivative of x of t with respect to time using a cosine omega t. The derivative of cosine is equal to negative sine, so this is going to become negative a, and I'm going to leave a space here, and then it's going to be sine omega t plus phi. Now the chain rule says I've just taken the derivative of sine with respect to its argument. Now I got to take the derivative of the argument with respect to time. That means the derivative of omega t plus phi, or excuse me, omega t plus phi. I need to take the derivative of that with respect to time, and that of course will give me omega. Oh, or that'll just make me erase everything. That gives me omega. Now I can take the second derivative. So the derivative of a omega sine omega t plus phi, we're going to have obviously a negative a and omega because they're just constants, so they can just come right out in front. And now I'm going to take the derivative of sine, which is cosine. There's the argument of cosine. Now I got to take the derivative of the argument, which is omega t plus phi. The derivative of omega t plus phi is omega. So I'm going to make this omega squared instead of omega. Okay. Now this one turns out to be equal to v, and this one turns out to be equal to a. Now, I wanted to write v of t, but I didn't have enough room, so I didn't write v of t, and I didn't write a of t either. But hopefully y'all understand that. Does that make sense to everybody? Remember, the first derivative is velocity, second derivative is acceleration. So this tells us something. This tells us, in fact, that this is obviously v max. In other words, the magnitude of the velocity is never going to exceed a times omega. And this one right here is a max. So that means the magnitude of the acceleration is never going to exceed a omega squared. So that's why I called it a max, but I just wanted to point that out. That's the way graphs of sines and cosines work. If there's a number multiplying it, normally the sine and cosine just vary between +1 and -1. But if you put a 4 in front of it, then it's going to vary between +4 and -4. Now, plugging those in, I get plugging these in, I get negative a omega squared cosine omega t plus phi plus k over m times a cosine omega t plus phi is equal to 0. Now, there is a common factor we can factor out of this, and in fact, it's going to be, let's do a cosine omega t plus phi, all of that times k over m minus omega squared is equal to 0. Since this is Newton's second law, it must be true for all t. So the only way that's true, notice a cosine is going to wobble back and forth, and various t's, there's no way you're going to always make that 0. So that means you've got to set this equal to 0. And you get, therefore, omega is equal to, and I'm just going to force it to be the positive, square root of k over m, just because the positive makes physical sense. Okay, technically the answer is plus or minus, but like I said, physically it doesn't make any sense to have something omega that is ultimately going to turn out to be related to the frequency of oscillation. There's no reason to make any sense out of a negative value. So that's it. So what we've learned now is that according to this type of differential equation, which is called the simple harmonic oscillator equation, okay, and it has that form and that form, you can see the square root of the constant is omega. So in other words, in this form right here, there's your constant. And that was k over m. I took the square root of it. That was the actual solution. So we now know that x of t is equal to a cosine square root k over m times t plus phi. If I take the most general case, another person came in. If I take the most general case, then what I get is, say, x prime of 0 is equal to x0, and x double prime of 0 is equal to v0. Well, what that means for this one is x prime, we already figured out, was negative a omega sine phi, and that's got to equal x0. And then this one is negative a omega squared. Whoa, whoa, whoa. Actually, sorry about that. Does anybody notice the boo-boo I made? That's not supposed to be there at all, so I'm just going to erase that. There's your x. And this should be your dot. I was going on derivative and not derivative, so I apologize for that. That was where the mistake was made, because I was remembering something else I just did earlier. So what we get here is not negative a omega. This one's just a, darn it. This one's just x0 is equal to a cosine phi. This one, on the other hand, is v0 equals negative a omega sine phi. Does anybody know why I have just the sine of phi, not the sine of omega t plus phi, or not the cosine of omega t plus phi? Anyone? Okay, it's because the t equals 0 was part of the initial condition. So I had to substitute t equals 0, which makes that whole first term inside the trig function to be 0. Now, if I take, let's call this equation 1 and equation 2, I'm going to take 2 divided by 1. And in so doing, what I'm going to get is v0 over x0 is equal to negative omega times, remember sine over cosine is tangent, so it's going to be negative omega tangent phi. So that means phi is equal to the tangent inverse of negative V0 over omega x0. So that's a general answer for any initial condition where they give you, the initial position x0 and the initial velocity v0. Now that we have that, you can also plug this back into here. So you can make, for instance, an imaginary triangle for which phi is that angle. And then, of course, what we mean by that is the top one could be, for instance, V0, because it's opposite over adjacent. And the bottom one could be negative omega x0. And then this, of course, would be the square root of V0 squared plus omega squared x0 squared. Whoa. So when I do that, it's going to get like that. So that's the hypotenuse. So you can now say that, for instance, if you want to solve for A is going to be x0 over cosine. But cosine phi is adjacent over hypotenuse, so that's negative omega x0 over the square root v0 squared plus omega squared x0 squared, like that. So that's the process that you sort of have to learn to work with differential equations. But the key thing is that you're not actually doing any of the major work with the differential equation. You just need to know what the answer is, and that's what we're giving you. So you don't want to focus on how did Mr. Younger get all this. No, you just want to focus on how are we going to use this to get an answer. Now, I ended up writing that way smaller than I needed to because I didn't realize I blew the page up. But we can now say A, since cosine is equal to negative omega x0 over all that stuff, if I divide all that, I'm just going to get basically the square root, let's say a negative square root v0 squared plus omega squared x0 squared. And all of that would be divided by omega. So that is how you could, for instance, deal with the initial conditions to figure out what A and theta is. You'd find even simpler cases in the first two examples. Remember, I just did what's called the most general case. If you did the first case, for instance, you just have x0 is equal to a cosine phi, which is like equation 1, but equation 2 would be really easy because it'd just be 0 equals negative a omega sine phi. So you choose sine such that, or you choose phi such that sine would be 0, which means you're going to choose 0 or pi or 2 pi or something like that, or minus pi. All of those are completely up to you. But again, that's the process. Okay. Does everybody understand that's how you do it? Once you see that differential equation, you're going to automatically say, this is my solution. And these two values right here are what I can use to figure out what A and phi are. And omega, of course, is the square root of the constant. If we have that form. So that's the whole thing about this. If someone actually physically asks you, hey, what's the actual solution to this, mass on the spring problem, you're going to write down x equals a cosine omega t plus phi. Then you're going to say, well, what's your initial conditions? and you're going to do some kind of trick like I did down there to find what A is and what phi is, or you can use exactly that A and that phi and do it accordingly, assuming that they gave you at least the X and the V at t equals 0. If they didn't give you it at t equals 0, then those aren't going to work, but it will work if they gave you the t equals 0 values. Does that make sense to everyone? Now that sounds kind of silly. Like why would we put so much time into studying this obviously simple case of a mass on a spring? Well, the answer is it turns out if you play with a Maclaurin series expansion, every function in existence has a Maclaurin series expansion that is like a constant plus 1/2 a constant times x squared. That's identical to a harmonic oscillator. Therefore, there's a lot of problems near equilibrium points where the function is just like a harmonic oscillator, and therefore it's going to behave like a harmonic oscillator. So that's why we study them, is because, like I said, a Maclaurin series expansion near a equilibrium point, in other words, near a stable equilibrium point, which would be like a minima in the potential energy function. So near that bottom part is always going to have a potential function equal to some constant plus 1/2 times another constant times x squared, which is just like 1/2 kx squared. So that's why that's valuable. The neat thing is that it turns out there's a lot of different equations that can be used and a lot of different physical problems that can be analyzed with this. So in your book, for instance, they go to an example. They say, for instance, let me see, I'll pull one up real quick. Determine the period and frequency of the car in example 14.1a. So in 14.1a, they said, okay, you have a 2,000 kilogram car and you've got 200 kilograms of people who are going to sit in it. When they sit in it, the car lowers by 3 centimeters. And they say using Hooke's law, F equals kx, and pretending like all 4 springs act like one big spring, figure out what k is. So that means you're going to put the 3 centimeters in for x. You're going to put 200 kilograms times 9.8 in for the force. And then you've got, 1,960 newtons is equal to k times 0.030 millimeters, or excuse me, meters. So let me write that down. What I'm saying is 200 kilograms times 9.80 meters per second every second is the weight. And that's going to be 1,960 newtons. F is equal to, in this case, we're just taking the magnitude, k times x. So that means if I take 1,960 newtons is equal to k times 0.0300 meters, then k is going to be equal to 1,960 divided by 0.03, and that gives me 6.53 times 10 to the 10 to the 5th. That's 1 extra sig fig, and that's newtons per meter. Then they follow up and say, what if you put 300 kilograms in? What would be the compression then? X equals question mark for W equals 300 kilograms times 9.80 meters per second. So 300 times 9.8 gives me 2940 newtons. We'll say 2940 newtons is equal to 6.53 times 10 to the 4th times x. So x is going to be 0.045 meters. And that's just what I get for solving for x. So that's a very typical problem. Now in this problem, they're saying, okay, now that we've done that, let's go back to that problem again. It says, determine the period and frequency of the car you just talked about after hitting a bump. Assume the shock absorbers are poor, so they really oscillate up and down. So what we're saying is, all right, for this next part, which is example 14-3, we're saying the whole car, which remember had a mass of 1,000, actually I said 2,000 kilograms, sorry about that, it's actually 1,000 kilograms. So M car is equal to 1,000 kilograms. M the people, actually no, I think it was 1,200, that's what it was, 1,200, my fault. Let me fix that real quick. So 1,200 kilograms. And then the mass of the people, which we'll assume the original one, is 200 kilograms. So that means mass total is equal to 1,400 kilograms. What they want to know is determine the period and frequency. So they want to know F equals question mark, and they want to know T equals question mark. Now, what we do know is we know that omega is equal to 2 pi times the frequency. We know that frequency is equal to 1 over the period, or we also know that the period is equal to 1 over the frequency. Okay? And we also know, because we just solved the harmonic oscillator problem, that omega is equal to the square root of k over m. So I can go ahead and calculate omega. Omega is going to be the square root of k over m. So that's going to be 6.533. I'm carrying 2 extra sig figs this time, times 10 to the 4th newtons per meter, divided by 1,400 kilograms. And what I'm going to do is say 6.533 e to the 4th divided by 1,400 equals the square root of 46.664 ... ignoring the units for right now. Now I'm going to take the square root of that, and that's going to give me 6.831. That's 2 extra sig figs, and that turns out to be in radians per second, just like it was in chapter 10 and 9 and 8. Okay, so now we can say F is equal to omega over 2 pi. So I'm going to say 6.831 radians per second divided by 2 pi radians per cycle, just so it sort of makes sense with the actual answer. I put that unit of radians per cycle because that's actually what it is. So I'm going to say divided by 6.8311 divided by 2 times 3.14159. And that's going to give me the frequency that I'm going to promptly erase, which equals 1.087 hertz. That's the units that we use. And these 2 sig figs are not sig figs, they're just numbers that we added on there. So that's the frequency. And then of course the period is 1 over the frequency. So I'm going to raise that to the -1 power, and that's going to give me 0.9198 seconds. That's 2 extra digits too. So there's how I finished that. See how I didn't know any of the details about that car. I just knew it's oscillating up and down. So I should be able to get some estimate of what the frequency is. Any questions on that? So hopefully you see that this equation's important, this equation's important, and this equation's important. Now let me show you all the other things. It turns out if you work a pendulum, a simple pendulum, then what happens is you have a ceiling right here. You have a string whose mass is negligible, and you have on the end a mass m. This is negligible mass. And the negligible mass is what makes it the simple pendulum. And what we're going to do is say that this angle right here is theta. Now, what we can see on here is we're going to have a force going upwards. That's the tension in the rope. And then we're going to have a force going downward. That's the weight, mg. And then, of course, we can see that this angle right here is theta. So that means this angle down here is also theta. Okay. So this little part that I have drawn up here is going to be mg sine theta. And this part right here is going to be mg cosine theta. Everybody follow what we did there? Okay. So if you want to talk about the distance traveled, we're going to have to talk about the little arc length s there. So what we'd say is Newton's second law, the summation of the forces is equal to m d2x over dt squared. But in this case, we're going to say, actually, I should say an r there so I can use a vector. But when I reduce it to one dimension, I'm going to say the summation of the forces is equal to m d2s over dt squared. S is equal to L times theta. So what we end up getting is the force acting on it is a negative mg sine theta is equal to m L d2 theta over dt squared, like that. Obviously, the mass is not going to matter because there's a mass on each side. I can now write it again. Let's write it this way. d2 theta over dt squared. Pulling the other part over there, that's going to become g over L sine theta is equal to 0. And this is not a simple harmonic oscillator. But if we assume theta is small, again, you can look at the Maclaurin series expansion, then sine theta is actually approximately equal to theta. So then we have d2 theta over dt squared plus g over L theta is equal to 0. Does this match the form that we had before? Remember, the form was second derivative plus a constant times the function that the second derivative is being taken of equals 0. So second derivative plus constant times a function equals 0. Does this match that form? It does. There's a second derivative. The g over L is the constant, and the function, which is what you're taking the derivative of, is theta. So anybody want to tell me what we're going to use as our solution? Theta of t is equal to what? So this is the abstract part. What did we say x of t was equal to? Everybody see it? A cosine omega t. So you can say A cosine omega t plus phi is the solution. And what's omega going to be? Can anybody tell by looking at this function? Or by looking at that equation in blue? So look what I wrote over here. Did I tell you anything about how to find omega? Anybody see this stuff? What about over here? Anybody want to guess what omega is now? Okay, omega is going to be the square root of g over L, because that's the constant in front of the function, period. If you really wanted to know why, you'd have to go ahead and plug in this solution, A cosine omega t plus phi, take the derivative, take the second derivative, plug it in, take the 0th derivative, plug it in, factor out the common terms, and then set that equal to 0, and you'd get omega equals or omega squared is equal to g over L. So that gives you omega's got to be the square root of g over L. And you can use your whole solutions, your initial value equations for A and for theta, all that stuff. So you see how it's just another instance of the harmonic oscillator? It turns out that you also can do the same thing for an equation like, for instance, what we call the physical pendulum. So if I look at a physical pendulum, what we're going to have there is a blob of matter. And let's say its center of mass is right there. And let's say the pivot point is right there. And let's say this distance from here to here is D. Actually, let's say L. Okay. So what that means is if we take the summation of the torques is equal to I times alpha, which in this case, we can't use a constant alpha. We're going to have to say the summation of the torques is equal to I times d2 theta over dt squared. In this case, the torque is going to be negative. We're going to have a weight hanging down here. That's mg. And of course, we're going to have to do L times mg sine theta, where of course theta is if you drew this line right here and you drew vertical right here, that angle is theta. So the torque is going to be L times mg sine theta. Then and of course with a negative, because when the theta is large or positive, the force is in the negative direction. When the theta is negative, it's in the positive direction. That's why the negative's there. So this and this come together to give us negative LMG sine theta is equal to I d2 theta over dt squared. If we assume theta is small, then sine theta is approximately equal to theta, and we can get negative LMG theta equals I d2 theta over dt squared, which can become d2 theta over dt squared plus I, oops, yeah, that works. Yes, I over mgl theta is equal to 0. Does this equation, does it match the form that we had on the simple harmonic oscillator? So the equation we just had, for instance, was this one. And the simple harmonic oscillator equation we had was this one. Notice a second derivative plus a constant times what you're taking the derivative of equals 0. Notice a second derivative plus a constant times the thing you're taking the derivative of equals 0. Second derivative plus a constant times the function you're taking the derivative of equals 0. You see that it matches? So someone tell me, what is the solution? Theta of t is equal to what? So remember what we did theta of t last time? What about the time before that? What did we do for x of t? Now, can somebody tell me what theta of t is going to be?
It is the A cosine
Exactly.
omega t plus that
Yep.
symbol.
Yeah. A lot of it's about the symbols, right? So yeah, that's the solution. How about this? This is a little harder. Can someone tell me what omega is going to be? So notice what omega became in this case.
Square root of g over L.
Right, it became square root of g over L. And where was the square root of g over L in the differential equation? Or excuse me, where was g over L in the differential equation?
Added.
So what do you think the omega is going to be here?
I over m.
Exactly. So I is going to, or the omega is going to be I over the square root of mgl. And if you look at your textbook, you'll see that's exactly what it is. They used H where I used L, but that's okay. It's the same thing. Okay. So that's a physical pendulum, same sort of solution. So we still have omega is equal to 2 pi f, which is equal to 2 pi over the period, all that kind of stuff. We still have the period is equal to 1 over the frequency, and the frequency is 1 over the period. In fact, there's another problem your book does, and in that case, it's called the torsion pendulum. And with that one, they use that the torque is equal to negative k times theta. And then you have d2 theta over dt squared times m is equal to negative k times theta, which gives me d2 theta over dt squared plus k over m theta is equal to 0. That's what happens for the torsion pendulum. And a torsion pendulum is just basically like, you can imagine an oil dipstick, you know how it's a flat piece of metal? You can imagine that hanging from the ceiling, and then hang a little barbell from the bottom of the dipstick, so that the bar of the barbell is parallel to the flat sides of the dipstick. And then if you twist it a little angle like that, it's going to come back with a torque that's proportional to how big of an angle it went through. And it's always going to try to pull it back to the equilibrium position. That's why you got the negative k theta. So this is a very normal looking problem. Can anybody tell me what solution you're going to use for that one? We did this one, and we got this. So what's the solution we're going to use for the torsion pendulum? So theta of t is equal to what?
A cosine omega t plus phi.
Yep, and I think specifically phi is the more correct pronunciation, but I still call it phi. Okay, how about omega? Can somebody tell me what that's going to be?
The square root of k over m.
Yeah, it's actually the same symbols that we used before in the very first one. So that's why all this stuff just repeats itself. You're just supposed to use this. In most cases, you're not even doing the initial condition stuff. You're doing stuff like, hey, what's the frequency? Hey, what's the period? That's it. Like if you look at the problem it gave us for the moment of inertia measurement, it says an easy way to determine the moment of inertia of an object about an axis is to measure the period of oscillation about the axis. Suppose a non-uniform 1 kilogram stick can be balanced at a point 42 centimeters from one end. If pivoted about the end closest to that point, it oscillates with a period of 1.6 seconds. What is the moment of inertia? See, they gave you basically F. They said they gave you T, which is 1.6 seconds. You can get F from that by doing 1 divided by 1.6. And then you can get omega from that by multiplying 2 pi times f. Well, guess what? That's also omega, which happens to be the square root of I over mgl. So now you can solve for I because you know m, g, and l. So that's what most of these problems are, and that's really what you're trying to do. Now, the damped harmonic oscillator, I want to go through this kind of quickly for you. So in addition to having the Hooke's law, in addition to having Hooke's law, you've got another force acting on it. So in this case, we have the summation of the forces is equal to negative kx and negative b velocity. So I'm going to say dx dt like that. And actually, I wrote it really badly, so let me make it better. So b times dx, there I go again, over dt. That's all equal to m d2x over dt squared. If you do like we've been doing, then that's going to give you d2x over dt squared plus b over m dx over dt plus k over m x is equal to 0. That's the differential equation for a damped harmonic oscillator. So this is the damped harmonic oscillator. Now this one you have to be a little bit more chinchy. Okay. In other words, you got to be a little bit more strict to really make it work out like you want it to. I mean, you can in principle do it with x equals a cosine omega t plus phi. It just turns out it's a lot more algebra. So if you revert back to what they taught you or what you would have learned in differential equations, you can find an easier way. So I'm going to do, say, let x of t equal a e to the rho t, because then x of t dot, which is the same thing as dx dt, is going to be basically the derivative of e to the rho t is e to the rho t times the derivative of rho t, which is rho. So I'm going to say a rho e to the rho t, and then I'm going to say x double dot of t, which is d2x over dt squared. That's going to be a rho squared e to the rho t. Now, if I plug all that in, I'm going to get a rho squared e to the rho t plus b over m a rho e to the rho t plus k over m a e to the rho t equals 0. I'm going to factor out a common term. That common term is going to be a e to the rho t. What I have left is rho squared plus b over m rho plus k over m, and that's it, is equal to 0. Okay. This equation, which is just like the one we had before, is actually called the auxiliary equation. Okay. And that auxiliary equation is, again, since the equation has to be true for all times, then this thing, the auxiliary equation has to be equal to 0. So that means rho squared plus b over m rho plus k over m has got to equal 0, which has a very specific solution. Rho is equal to negative b over m plus or minus the square root of b over m squared minus 4 times 1 times k over m, all that divided by 2, which ends up becoming negative b over 2m plus or minus, I'm going to absorb that 2 into the denominator of the square root. So it's going to become a 4 inside. So I can write this as b over 2m squared minus k over m, like that, because the b, when it hit that term, canceled out with the 4. That's really wonderful. Okay. Now, your book is using something a little bit weird. It's saying the conditions are b squared is greater than 4mk. It's saying b squared is equal to 4mk, and it's saying b squared is less than 4mk. Remember, that's the thing that makes the thing under the square root possibly 0 or even a negative number. Well, because of that fact that that an I in the exponent of an E can give you a relationship like sine or cosine, it turns out the only way we get a solution that oscillates back and forth like that is if the square root is a negative, is taken of a negative number. So in other words, when b squared is less than 4mk, then the square root of b over 2m squared minus k over m is equal to I times the square root of k over m minus b over 2m squared. Okay, so this process is going to be called underdamped, because it's going to make an actual sinusoidal or cosinusoidal curve. This case is going to be critically damped. And the reason why is it's the critical condition where the denominator, or excuse me, where the square root is 0. So it turns out when you have a second order differential equation, you need two linearly independent functions to correctly state the actual equation or solution for the differential equation. In this case, when b squared is equal to 4mk, you're going to get a 0 under the square root. So the square root would be 0, and you'll just get one solution, negative b over 2m. That means you only get one equation, so it's not good. Well, the method then is, according to a differential equations class, you have to multiply it by the lowest order polynomial that would work. In this case, you'd say the polynomial would be C1 plus C2 times t. So we would say x of t is equal to e to the negative b over 2mt times C1 plus C2t, like that. So that's the actual equation. And what you'll notice is your textbook author does not give the solution at all, because he's never going to ask you for it. Okay, it's just going to be a graph, and what he could possibly do is ask you what value of m is going to make it the critically damped, what value of m is going to make it the overdamped, or in this case we have the overdamped case. Now, in the overdamped case, we actually get a positive square root, and the problem with a positive square root is it's just not going to be sinusoidal. So we end up getting x of t. Actually, let me write it in the same color I've been doing. In this case, I'm going to get x of t is equal to a times e to the negative b over 2m plus square root, all that times t, plus another constant, let's say c, times e to the positive b over 2m plus square root times t. That would be the solution. Again, this is one your textbook author does not give you, because it doesn't matter. We're not going to ask you to do that. We are going to ask you to do this one, the critically damped case, and the critically damped case gives us x of t is equal to a times e to the negative b over 2mt. So notice that's just an exponential decay, because b and 2m are all real numbers. And then what you're going to get is c1e to the positive square root k over m times I, by the way, minus b over 2m squared times t plus c2 e to the negative I square root k over m minus b over 2m squared times t. And that ultimately can just turn into cosine of that nasty square root times t plus phi. And in fact, they call this nasty square root omega prime. Okay, so omega prime would be equal to the square root k over m minus b over 2m squared. Okay. So you could just go with the same process like we did before. It can ask you questions about, A or about omega prime. In fact, one of the problems is just wants you to know the difference between omega and omega prime. Remember, omega was the square root of k over m. In this problem, we got the square root of k over m minus all that stuff. And you're going to see that it doesn't differ very much. But that's basically the whole process with a damped harmonic oscillator. With the forced harmonic oscillator, the only difference is instead of 0, you would have f is equal to f0 cosine omega t, like that. And your book gives you a very specific solution for when that happens, and that's all you do. It's no big deal. Okay. All right. So what I'm going to tell you is, as I said, I want you guys to work on your practice midterm, which I'm going to fix right after this. And I want to see everybody getting at least a 90 or higher. If you score a 90 or higher at least once, then I'm not going to put chapters 14 and 15 on the final exam. Okay? So I just want you guys to score a 90. Well, let's say a 90. Is that high enough? Is that too high? Let's say an 85. Okay, I'll say an 85 or higher. So if you score an 85 or higher and everybody else does the same, then I'm not going to put any questions on the exam that are related to chapters 14 or 15. What happens in the event that I do put those questions on there? Well, let me show you. It's not going to be as big a deal as you might think. I'm going to go to my quizzes and I'm going to pull this open. Let me kill this sharing that I'm doing. Go ahead and text me your first, or excuse me, chat me your first and last name if you haven't already. That way I'll have you for roll. Now I'm going to open this and now I'm going to share screen, and this time I'm going to share. There it is. Okay. So I want to show you the types of questions that are most important from chapter 14 and 15. And I'm hoping I'm seeing them. I saw down here 14, but I don't see the one I was actually looking for, but that's okay. I can go with it anyways. So this is a lot more questions than I meant. Oh, entirely wrong textbook. So that's a whole different story. Let's check over here. And that's exactly the problem that happens with those tests. That's why, you see all these banks here and you think they're all available, but then when you go to pull them up on the test, they're not really available. So let's do this. I'm going to go to an entirely different class. Let's go to this class. And now, there it is, the easy questions. Okay, so look at chapter 14. This is the kind of stuff I want you guys to be able to do. So let me make this as big as I can. So notice this question right here. It says the maximum speed of a 3 kilogram object in simple harmonic motion is 4 meters per second. The maximum acceleration is 5 meters per second. What's the period of simple harmonic motion? And I gave you this ginormous hint right here. X is equal to a cosine omega t plus phi. So velocity is equal to dx dt equals negative a omega. And acceleration is the second derivative, which obviously that's a typo, but that should be a dv dt. I don't know how that turned out that way, but it's not right, and it's repeated that way. So anyways, this is a and negative a omega squared. That tells you negative a omega squared, or the a omega squared, is the largest acceleration. So what I know is the 5 is equal to a omega squared. And what I know is the 4 is equal to a omega. So from that alone, I can figure out that let's do a different share again. Okay, so what we just found was 4.00 meters per second is equal to A omega squared. Notice it was positive, so I just threw the negative away. That was actually equal to A omega, not A omega squared. The 5.00 meters per second squared was equal to A omega squared, which, by the way, is A omega times omega. So I can just say now that 5.00 is equal to 4.00 times omega. That tells me omega is equal to 5/4, which equals 1.25 radians per second. So that's all I had to do with that to figure out omega. But what they were asking me for was, what is the period of simple harmonic motion? Okay, well, omega is equal to 2 pi f, which is also 2 pi over the period. So that means the period is 2 pi divided by omega, which would be 2 pi over 5/4, which would be 8 pi over 5. If I compute that, 8 times 3.14159 divided by 5, that gives me about 5.02. Six, 5 seconds. And now if I stop sharing that and I click over to start sharing this again, you can see 5.03 seconds is the right answer. See how that works? So these are the types of problems you need to be able to do. You need to be able to identify what omega is, identify what A is, identify what phi is, find the period from it, from the frequency from it, that kind of stuff. That's really all you have to do. You can look, these other problems are the same way. I'm gonna have to go in and fix all these, which really stinks because that's a lot of problems. But either way, I think y'all, hopefully y'all would have caught that. But this is another one. They gave you the mass. They gave you the amplitude. So that means A is equal to 6.00 meters. The maximum acceleration is 5 meters per second squared. So in this case, you got A equals 6.00 meters, and you got A omega squared is equal to 5. So you can combine those two to figure out what omega is, and they want to know what is the period. So again, you do it just the same way. Does that make sense to everyone?
Yeah.
So it's pretty straightforward. Let me show you something else, which I think that's enough. Yeah, I'll leave it at that. And we're actually out of time anyways. Hey everybody, so I'm going to definitely fix this final in about 2 minutes. Okay, so if you've already chatted me your first and last names, you guys are free to go. As I told you, you can take your exam on Monday with me at 5:30 if you'd like. Otherwise, you can take it Thursday with Miss Raskovic at 7 p.m. That's pretty much your only choices for you or for the 242 class. But if that doesn't work for you, then you can take it at any of my class times, which Wednesday at 9 a.m., Wednesday at 10 a.m., Wednesday at noon, and Wednesday at 2. Those are options. And then Monday, the 29th, you have the options of 9 a.m., 10 a.m., 12, and then as I told you today, 5:30. Just let me know if you're wanting to take that, because I'm not going to stick around on Monday. unless someone confirms that they want to take it that time. I don't mind sticking around for anybody that wants to take it. I just, like I said, I'm not going to stick around if no one says they're going to take it that time. So just let me know if you're not planning on taking it with Miss Raskovic, and let me know which time you want to take it. And that's it. You guys are free to go. I've enjoyed having you. And you shouldn't have to come to any more classes, but you're welcome to. So if anybody needs to see me, needs some last minute questions, just send me a chat or a text message. And I will sign on at 5:30 on Wednesday. Otherwise, I'm not going to even bother signing on. Same thing with Monday. I'll sign on at 5:30, unless, like I said, unless no one contacts me. All right, you're free to go. Thank you, everybody.
Thank you.
Thank you.
Thank you.
So basically what you're saying is you're not teaching anything on Wednesday where we're done?
Yeah, you're done. If I would have covered chapter 15, but I'm really trying to get you guys to not have to be tested on that on the final. So just take the practice test. You'll get plenty of practice on the 14 and the 15.
Okay.
Yep. But like I said, if you want some more information on it, I think you can pick up the simple questions that I choose. I think you can get those just from looking at the examples in the book. If you have a problem, just let me know. I'll teach it to you. I was going to do it tonight, but we ran a little over. So
And then you said just chapters 14 and 15 for homework that need to be turned in?
yeah, just make sure you get your homeworks done, ideally by the 28th at 11:59 p.m., but I'm probably going to allow you to the 29th at 11:59 p.m. So I want
Okay.
that done, and I want you to score at least an 85 once on the practice final. If you do that, I'll be content and not test you on chapters 14 or 15 on the final.
Okay, cool.
Right? And you'll have this in documented form on my YouTube channel right after class is done, or sometime tonight when I post it.
All right.
All right.
Thanks.
No problem. See you, Caden.
So, sorry, can you hear me?
Yes, I can hear you. Go for it.
So, um, you say so it had to be the whole class that got at least an 85 on the practice for the final, so that you won't put the chapter 14 and 15 in?
Yeah, that's ideally each student that actually has been taking tests and hasn't missed a bunch of tests. Obviously, I've got some students that just sort of disappeared, so I'm not going to require that they do it. But if everybody gets an 85 or higher at least once, then I will not put 14 or 15 on there.
So
And
the
I'll let
whole,
you know. I'll know by Friday probably. I'll definitely. If everybody does it immediately, I'll know really soon. I'll let you know as soon as they do it.
so the whole class have to. So, yeah.
In principle, yes. Sometimes Mr. Younger's a little more fair than that, so just do your best and everybody try to get an 85 or higher.
Okay.
The more you
So
take that final, the practice final, the more better prepared you'll be on the final.
so the bonus question, the bonus grade for like the practice test,
Mhm.
is it just under the all the tests under the practice test section, or is it under chapter practice? Because I've been doing the chapter practice. I do some of the practice tests, but I've been doing mainly the chapter practice.
The chapter practice is well, it's not very good for chapter 15 for you because 15 and 14 covers a lot more material than I'm requiring of you, so they're not very good for that. But in general, the chapter ones do better prepare you, but they don't count on anything for the extra credit. So the practice tests, I look in your grade book and it shows your practice test average, what I do is I take that percentage and divide it by 20, and that's how many points I just add to your final course grade.
Okay. Also like for the homework, I don't know why, but I got like chapter 42 or something on it.
Yeah, those
And
are all extra credits where you can just get extra points for doing them.
so is chapter 36 also extra credit then?
Yep. In fact, all I told my students was all you had to do was 1 to 11, 14, and 15. Anything other than that is extra credit.
So does that extra credit for like
The
the average for like the
So the
class?
way the extra credit works for the homework is supposed to work is each time you have an extra credit, that you done at like an 80% or better, I'm going to replace one of your scores that's not a 100 with a 100. But when I do this and you do a lot extra chapters, I look for other ways to give you extra credit too.
Okay, so can you like any chance I can get the practice test for like the last practice test unlocked? Because like I didn't realize that you wanted us to do the practice test for it, and I was doing like just the chapter practice test.
Yeah, I can't open it back up. The whole purpose of me giving you extra credit for that is so that you'll do better on the test. So I'm sort of shooting myself in the foot if I let you take it after the test has already been taken. So
Oh, okay.
but yeah, just make sure you pay a little closer attention in the future, because especially if you get me for 242, I do the same thing in there. So just make sure you sort of pay attention to exactly what the extra credit is and how it works and that kind of stuff, or make sure you ask me if you don't understand.
Okay, so if we'll get 85 on the final practice test, then there's no chapter 14 and 15, just 1 to 11.
Exactly.
Got you. Got you.
And
All right.
even if I do 14 and 15, they're going to be pretty easy ones.
Okay.
Okay.
All right.
All right. Have a good one, man.
Thank you. Bye.